All right, so we will begin working on the limit process for finding the area under the curve. And this will lead us to eventually doing what we call definite integration. Now, when we do the limit process, you're going to have to be familiar with summation formulas. So I have highlighted, there are 4 of them. And when you do the summation of a constant, you take that constant times your number of counters. So, for example, if you were summing up 3 and you were doing that from I equals 1 to 5, what that means is you'd be adding up 3 5 times. So 3 plus 3 plus 3 plus 3 plus 3. Well, a quicker way to do that would be simply to take your constant 3 times your counter, so times 5, and get your 15. So there's summation for a constant. If you are doing a summation and you have your I, you have the actual counter that you're doing the summation with. So it's going from 1 to 2 to 3. And so you're going 1 plus 2 plus 3 plus 4 plus 5. You can actually calculate that by doing this top value times 1 more than that top value and dividing by 2. Likewise, if your counter is squared, so 1 squared plus 2 squared plus 3 squared, and so on, all the way up to n, you can calculate that using this formula. And the same thing with your counter to the 3rd power, this formula. Now, these formulas, I would like for you to know them. I know we're not going to have as much practice with them this year, so I may have to give them to you, but I definitely want you to be familiar with how to use them. So we're going to use the limit process to find the area of this y equals 25 minus x squared between that curve and the x-axis. Now our interval this time is from 1 to 4. So it is not 0 to 5 as is shown. It is from 1 to 4. So we're actually finding the area of this shaded region right here, going from 1 to 4, finding the area here. And notice that I'm not giving you any rectangles to work with. So we have our A, which is 1. We have our B, which is 4. And our number of rectangles, n, is unknown. Now, I'm going to encourage you that even though I have given you a whole page, that you write small, because you will use this entire page to do your algebra for this. So our delta x is, as before, b minus a, so 4 minus 1 over n. It's just that this time we don't know the n, so our delta x is going to be a variable 3, or a variable expression, 3 divided by n, 3 over n. Now, when you're doing the limit process, we don't have to use both endpoints. We just pick one. So we're going to use the right endpoint because it's easier. So for the right endpoint, I'm going to give myself some space here. Our mi is found by doing a plus I times delta x. Well, a in our problem is 1, and our delta x is 3 over n. So it's 1 plus 3 over n I, or you might even say 3I over n. I would probably say it that way. 1 plus 3I over n. All right, so we are going to do the summation process, finding your area. Now this time, instead of starting right off with the summation, we're doing the limit as n approaches infinity. So the limit as n approaches infinity. Then we'll do our summation symbol. So we're doing the sum from I equals 1 to n. Our number of rectangles is unknown. F of 1 plus 3I over n. So this is our value that we'll substitute in for x, times our delta x, our width, which is 3 over n. And again, hopefully that width makes sense to you. Your 3 would be the total width of that x-axis, and you're dividing it up into n rectangles. So 3 divided by n would be the width of each rectangle. Now I'm going to do maybe 1 or 2 more lines on this, and then I'm going to switch to my completed notes so that you can see the algebra with a little bit better handwriting. So our area is going to equal the limit as n approaches infinity of the summation from I equals 1 to n. And so now we're going to use our equation. So it'll be 25 minus our x, which is 1 plus 3I over n. And that needs to be squared. And then we'll take all of that times 3 over n. So I've made my substitution into the function. My next step is going to be to work on this 1 plus 3I over n squared. I'm going to work on this part of the expression to simplify it. And at this point, I'm going to switch us over to the completed notes and go through my different lines, just because the ability to write small enough is going to be difficult for me. So switching over to these notes, and I'll clear my ink to get that out of the way. And we're here on the back, and I will keep you filled in where we are in this process. So right now we are looking at this line. This will be the next line that you'll do as you multiply out 1 plus 3I over n to the second power. So taking it times itself, you would have 1 plus 6I over n plus 9I squared over n squared. Now, I realize that you have to write down the rest of this. So you're doing the area by doing the limit as n approaches infinity of the summation from I equals 1 to n of 25 minus, and then our multiplication in parentheses, and then times the 3 over n. So as I move to my next line, so now I'm on this blue arrow line. Notice that I've just combined like terms, 25 minus 1, giving me 24. I've also distributed this minus sign so that I have minus 6I over n and minus 9I to the second over n to the second. So again, I'll give you time to get that line down. The limit as n approaches infinity. I did do one other thing. I also moved to the outside of the summation, but after the limit, I moved the 3 over n. Any factor that does not have an I can be moved outside of the summation symbol. So I moved the 3 over n. And then we're going to move to the next line. I'll do it in green. This time I'm going to use this idea of distributing the summation symbol. So notice that I kept the 3 over n after the limit. And now my summation symbol I have distributed. So I've distributed the summation, first of all, to the 24. So I have the limit as n goes to infinity of 3 over n. And then I have the summation from I equals 1 to n of 24. Now, I am pulling out 6 over n. So notice that that is in front of the summation. And then I have the summation of I equals 1 to n of I. And likewise, I pulled out 9 over n squared, so that I have the 9 over n squared, and then the summation from I equals 1 to n of I squared. And I'm doing that step. That step's a very important step, so I'm going to put a star by it. This line right here is very important because I have now produced 3 summation expressions that I can replace with the definitions that we had at the top here. So where I have your constant, where I have this n times n plus 1 over 2, I can use what I have created here. So that line transitioning to this next line, which I'm going to go back to red, transitioning to this line, these would be, I think, key steps in doing this process. So notice that the 3 over n has not moved, but I have in this line removed the summation symbols. So for a constant, the summation just becomes 24 times that top variable, 24n. For the summation with an I, it became n times n plus 1 over 2. And notice that the 6 over n is here on the outside. Don't do the canceling just yet. That's really the next line. And then for my I squared, my replacement is the n times n plus 1 times 2n plus 1 all over 6. And that then is multiplied by the 9 over n squared. Now, after this, the summation symbols are gone, and you may not like it, but you can certainly do it. You have algebra after that. So you're working on canceling. You'll see that I did some canceling so that I got my next line that I've marked in blue, canceling the n's in my second term right in here, canceling the n's and the 3 into the 9 and the 6. So some cancellations allowed me to go from my line marked in red to my line marked in blue. I also multiplied out the n plus 1 and the 2n plus 1 to get 2n squared plus 3n plus 1. You often will have to do that. So we're going to continue, and I'm going to keep using blue because the rest of what you're doing, you can kind of get a feel for what you see to do. I definitely did the distributive property and separated each one of my fractions. And then I started working on combining any like terms that I could find and simplifying my fractions as much as I could. Now, I wrote over here your goal, so you'll know where you're headed with this. Your goal is to have each term either as a constant, so that means no variable at all, or as a fraction within only in the denominator. We do not want to have any n's remaining in the numerator. So notice that I kept my 3 over n outside of any work I was doing inside the bracket until I got to this line. Now I'll mark it in green so you can see what line I'm referencing. So once I had simplified and combined like terms as much as possible, then I distributed 3 over n. And it's at that line that I've marked in green that I have reached my goal of having either constants or having expressions where n or a power of n is in the denominator. And then I'm going to ask you to recall that we had a theorem that stated if we had a constant divided by n and n went to infinity, thinking about it kind of like winning the lottery, that you had 0 chances. And so notice that in this line, I got rid of my limit symbol because now I'm doing the limit. So 63, and then I have 9 over n, that's 0. Then I have minus 9. 27 over 2n, that is 0. 9 over 2n to the second, that is 0. And so I end up with 63 minus 9, and my final answer is 54. And the area under the curve is exactly 54 square units. And that is what we are calculating when we do numerical integration, but through a limit process. So we created infinitely many rectangles so that the width of each rectangle actually became irrelevant. And that's the idea that integration is based upon. So you'll have some problems to do where you know your number of rectangles. For that, you can use a calculator. And I think you have 3 of these problems where you do not know your number of rectangles. You will need to be prepared to use the summation formulas. These are the only ones that you will need. And you should expect this much work as you go through that limiting process. So good luck to you. Be sure that you reach out to me if you have any questions.